Okay, we are discussing a data structure called BDD or in particular ROBDD, reduced order binary decision diagram, by which we can represent our any Boolean function. Also, we have seen some algorithm by which we can manipulate the BDDs, okay, like reduce, apply, restrict, exist, like that. And on the other hand, we have seen that any digital circuit can be represented by Boolean expression, and that Boolean expression can be represented by ROBDD. And we have seen that with a particular variable ordering, the BDD representation of any function is unique. Okay, today we will see how we are going to represent the sequential circuit. Okay, so how we are going to use bordered binary decision diagram for sequential circuit. When we look into the sequential circuit, then we will find that, or we can see that it can be represented with the help of a state transition diagram. Okay, so basically it says that my system is in a particular state. Depending upon the present behavior and the input sequence, it will make a transition to the next step. Okay. Now, we have to represent those particular transition when we are going to talk about the sequential circuit. And basically sequential circuit will be represented by the state transition system or state transition diagram. Okay, now just see this particular case that I am having a state transition system. It is having 4 states S0, S1, S2 and S3, and we are having those particular transition. I am having a transition from S0 to S1. When we are in the transition S1, then we can make a transition to S3. If I am in the S3, then it will remain in S3. On the other hand, from S0 we can go to S2, and from S2 I can go for S3. So, this is a state transition diagram, and we know that if we are having a state transition diagram, then we can synthesize the sequential circuit for that particular state transition diagram. So, in this lecture we are going to see how we are going to represent those particular state transition system with Boolean function, and eventually we are going to represent those particular Boolean function with the help of OBDDs, ordered binary decision diagram. Okay. To represent this particular state transition system, say it is having 4 different states. To represent this particular 4 states, we need at least 2 state variable. With the help of this particular state variable, we can represent this particular state of this particular state transition system. So, if in general, if a particular state transition system is having say number of states is equal to n, then the minimum number of state variable required to represent this particular state transition diagram is ln n, that means log 2 to the base 2 n. So, this is the minimum required number of variables that we need to represent this particular system. Okay, but we may take more state variable also. So, depending on that, the state encoding will be different. Now, since I am going to say that we need at least log n to base 2 number of variables to represent n states. Since we are having 4 states over here, so at least we need 2 state variable, and we are representing this particular state variable as say x1 and x2. With this particular state variable, we can represent this particular 4 state, because we are having 4 different combinations 0 0, 0 1, 1 0 and 1 1. With this particular 4 combination, unique combination, we can represent this particular 4 states. Okay. So, this is basically now we are going to say that with the help of this particular state variable, we can say that the state S0 will be represented by x1 bar, x2 bar. That means, we can say that when both are 0 0, we are going to represent the state S0. So, S1 will be x1 bar, x2. That means, we can say this is your 0 1 state encoding. S2 is x1, x2 bar. That means, state encoding is your 1 0, and S3 is your x1, x2. That means, this is the state variable is 1 1. Then we can say that these are the states for this particular state S3. So, we need at least 2 state variables to represent those particular 4 states. And already I have mentioned that in general, if I am having n different states, then we need log n to the base 2 number of variables, ceiling of that particular thing. That means, log 2d base 2 n, and I am going to take the ceiling of that particular values, and this is the number of variable required, minimum number of variable that we need to represent the state and different state uniquely. Okay, so, for this particular state transition diagram, I am having 4 different states, and these are the state encoding of this particular 4 states. Now, when we are going to talk about your state transition system, we are having 4 different states, say S1, S2, S3, S4. Sometimes we are interested for the set of states. I am going to say that the set of state is your say S1, S2. Sometimes I am interested to look for the set of state S1, S3, S4. That means, you can see that these are the power set of this particular set of states. Okay, I am having a set of state as your S1, S2, S3, S4. This is the set of states. So, I could say that this is your S. Then, what are the set of states? What are the different subset we are going to get? This is nothing but the power set of this particular S. That means, we are going to get 16 different combinations. Now, how to represent those particular set of states? We are going to see this particular scenario. Now, come back to this particular previous state transition diagram. I am having this state as S0, S1, S2, S3, and these are the binary state encoding for this particular 4 state S0, S1, S2, S3. That means, this is your x1 bar, x2 bar, already I have mentioned this is 0, 0, 0, 1, 1, 0 and 1, 1. Now, when we are going to look for the set of states, so I can talk about that S0, S1 is a state of state. S0, S2 is a state of state, like that S0, S2, S3 is a state of state. Now, I can represent all those particular state of states with the help of Boolean expression, because S0 is represented by x1 bar, x2 bar, and S1 is represented by x1 bar, x2. So, this is x1 bar, x2 bar plus x1 bar, x2. Similarly, S0, S2 is yours x1 bar, x2 bar plus x1, x2 bar. Now, if you see these things, say these are the representation of the state of state, it is representing 2 state S0, S1. Similarly, this expression is representing these particular 3 states S0, S1 and S2. And if you look this particular right hand side, you will find that these are nothing but Boolean expression. Okay. Once we have this particular Boolean expression, then what we can do? We can construct BDD for those particular Boolean expression. Now, you just see that the state of states can be represented with the help of BDDs, or in particular we can say that ROBDDs, reduced ordered binary decision diagram. And the representation, we are going to get an unique representation if we are stick to a particular variable ordering. So, now, if we are having some states, if you consider subset of those particular set of states, then what we can do? We can represent those particular subset or set of states with the help of a Boolean expression, and we can convert this particular Boolean expression, or we can represent this particular Boolean expression with the help of ROBDDs. That means, ROBDDs can be used to represent set of states. Okay. Now, in nutshell, what we can say that if we are going to look into a state transition system is nothing but the set of states and one transition relation. Okay. So, basically we can say that this is basically state transition. These are the 2 basic components, set of state and the transition relation. Now, we have seen that this set of states can be represented with the help of Boolean expression, and once we are having the Boolean expression, that Boolean expression can be represented with the help of OBDDs, or you can say that ROBDDs if we stick to a particular variable ordering. Okay. Next, we are going to see how we are going to represent this particular thing. So, in this particular case, just a simple example I am showing over here. Say this is the set of state, I am going to take S1, S2. So, this is the Boolean expression for this particular subset S1, S2, x1 prime, x2 plus x1, x2 dash. So, this is basically S1 is your 0 1 and S2 is your 1 0. Now, once I have this particular Boolean expression, we can construct the ROBDDs for this particular Boolean expression, and we are going to get this is as our Boolean ROBDDs for this particular Boolean expression. That means, these ROBDDs are going to represent the set of state S 1 and S 2. And what is the variable ordering over here? I consider the variable ordering is your x 1, x 2. This is the variable ordering we are using to construct this particular BDD. And if you look into this particular BDDs, you will find that no more reduction can be applied to this particular OBDDs. So, ultimately we said that this is the ROBDD representation for S 1 and S 2 states. Similarly, this is the another ROBDDs. This ROBDD represent the subset S 0, S 2, S 3. So, with similar encoding that we are having. So, we are going to look for the subset which consists of state S 0, S 2 and S 3. Since we know the binary encoding, we can write down the Boolean expression this particular subset. One, we have this particular Boolean expression, always you can construct the ROBDDs for this particular Boolean expression, and eventually if you try it, if you try to construct it, then you are going to get this particular ROBDDs for this particular Boolean expression. And the variable ordering, again we are choosing for this particular order BDD is your x 1, x 2. Okay. So, with this particular variable ordering, we are getting this particular BDDs, and this is basically ROBDDs for this particular subset, because we cannot apply any more reduction rules to this particular BDDs. So, we are getting the ROBDDs. So, like that, if we are having a state transition system, we are having several states. All those particular states can be represented with the help of an ROBDDs, because those particular states can be represented with the help of Boolean expression. Secondly, if you take any subset of those particular states, then what will happen? Again, we can write the Boolean expression for those particular Boolean subsets, and this Boolean expression can be represented with the help of your ROBDDs. So, we can now say that the set of states can be represented with the help of ROBDDs. Now, when we are going to have a set, we are talking about the set. When we are having this particular set, then generally we can apply some set theoretic operation on set. Say, if I am going to consider two set S 1 and S 2, generally we can construct S 1 union S 2, S 1 intersection S 2, like that, set difference S 1 minus S 2, like that. If we are working with the set, then we can perform some set operation on those particular states. Now, these particular states S 1 and S 2, we are representing with the help of ROBDDs. Now, say if I want to take the union of these two sets, now can we work with those particular ROBDD representation? If we want to take the intersection, can you use those particular ROBDDs to get the intersection of these two states, or whether first I have to construct the first I have to calculate the union, then construct the ROBDDs. This is also you can go. So, we know S 1, we say it is your say S 0 S 1, we know S 2, then we know say this is S 1 S 2. So, if I am going to say that S 1 union S 2, then basically I can say that this is your S 0 S 1 S 2. So, first I can calculate this particular union, then I can construct the ROBDDs for this particular union. But if I am already having the ROBDDs for these two particular sets, whether can I use some algorithm or use some operation, so that I can directly going to get S 1 union S 2. It is possible. Okay. So, how we are going to do it? Say S 1 and S 2 are two sets. Now, we are going to say that B S 1 and B underscore S 2 are the OBDD representation of set S 1 and S 2 respectively. So, as B S 1 is the ROBDD representation of S 1 and B S 2 is the ROBDD representation of S 2. Now, if we are going to take the union of this S 1 and S 2, then we can construct it with the help of this operation. Already we know the apply algorithm, apply with some operator can be applied with the help of this apply operation. So, we are going to apply the operator is your plus B S 1 and B S 2. Now, this operation after constructing this, after applying this particular operation, what will happen? We are going to get an OBDDs, and that OBDDs are going to give me the set of state basically, and it is going to say the union of S1 and S2. Okay, because it is going to take the common portion of from BS1 and BS2. You can construct. Similarly, if I am going to perform the intersection of S1 and S2, then we can apply this particular operator, apply dot BS1 and BS2. So, by application of these things, we are going to get the OBDDs for S1 intersection S2. So, you just see that if I am having a BDD representation of two sets, then I can use this particular apply operation on that to get the union and intersection of these two states. Already I have mentioned that when I use this particular apply operation, I am going to get an OBDDs for this particular operation S1 and S2, and the variable ordering of this particular resultant OBDDs will be the same with your BS1 and BS2. Again, you should remember one thing, when we are going to use this particular apply algorithm, both the BDDs must have computable variable ordering. That means, they should have the same variable ordering, and the variable ordering of our resultant BDDs is also same with those particular input BDDs. But whatever OBDDs we are getting, it may not be reduced one. So, after that what happens? I can use this particular reduce algorithm to get RO BDDs for this particular intersection operation. So, if we are having BDD representation of, also in particular I can say that order BDD representation of two sets, then I can use this particular apply operation, apply algorithm to construct union of these two states or intersection of these two states. Like that we can construct other operation also. So, this is one advantage we are getting. Okay. Now, what will happen? We have discussed, we have talked about the state transition system. Basically, we have seen that in state transition system, it is a collection of some states, and we have discussed how to represent those particular states with ROBDDs, how to represent the set of states with the help of ROBDDs. Now, when we talk about the state transition system, then we are having another component which is your transition. Basically, say this is your state S0 and this is your state S1. Now, we are having this particular transition. We are having a transition from S0 to S1 in our state transition graph. Now, our aim is to we should look for how to represent this particular transition. Okay. Then, if we can represent this particular transition, then what we can do? We can represent the entire state transition diagram, because the state transition diagram is nothing but the collection of those particular transition. Now, when we are going to look into this particular transition, then it can be viewed as an order pair S0 and S1. Okay. We can say this particular transition is an order pair which is a collection of two states, and here S0 it is having a transition from S0 to S1. So, we can say that S0 is the current state or present state of my system. Once it make a transition, then it will go to the S1, then I will say that this is your next state of my transition. So, that is why I am saying that this transition can be represented with the help of an order pair SP and SN, where SP is the present state and SN is the next state. So, with the help of these particular things, we can represent the transition, and once we collect all the transition, then we are going to get the entire state transition diagram or behavior of state transition diagram. Now, we are going to see how these particular transitions are going to represent it, or how we can capture this particular transition. So, in this particular case, if already I have said that if we are having some n number of states, then we need total or minimum number of state variable as your log n to the base 2. Now, we just said that we are having a state transition system where n variables are used to represent the states. So, we can say that these are the state variable x 1 to x n. So, these are the state variable required to represent a state, and I will say that this particular state variable is representing the current state or present state. My system is in a particular state in a particular instance of time, and I am going to say that in which state I am or in which state my transition system is. I am going to represent this with the help of those particular state variable. By the evaluation of this particular state variable, it is going to give me the current state. Now, when I am having a transition say from one state S0 or say SP to S and present state, then we have to represent this particular next state also, where we are going to, after making this particular transition, I say that this particular next state behavior will be again represented, next state will be again represented with the help of n state variable, because this is n state variable is required to present this particular present state. I need another n state n variable to represent this particular next state, and I will say that the prime version of the original variables are used to represent this particular next state behavior. So, if I am having an x1 variable which is related to your present state SP, then corresponding to S1 I am going to one variable, I will say that this is one x1 prime, which will represent or which will use to represent this particular next state. So, that means we need another set of state variable to represent this particular next state. So, we are now having the representation of the present state, we need n variables, we are having the representation of the next state which involve another n variables. So, that means we need total 2 n variables. So, that means if we are going to use n variable to encode our states to represent this particular transition, we need 2 n variables, because this is nothing but the combination of present state and next state. N variables are used to represent the present state, another n variable will be used to present the next state. Okay. So, we need 2 n variables. So, if we are having x1, x2, x3 like that, x n as the present state variable, then their prime version will be used to represent the next step. And combination of this particular variables are going to use or going to represent our that particular transition. Okay. Now, we are going to see this particular representation with the help of our earlier example. What we have seen, that this is the state transition diagram, it is having 4 states S0, S1, S2, S3, and these particular states are represented with the help of this particular state variable, and this is the binary encoding of this particular states. Now, we are having some transition. So, 1, 2, 3, 4, 5, we are having 5 transitions, so transition T1, transition T2, transition T3, transition T4 and transition T5. When I am going to represent this particular state transition system, we have to represent those particular transition. Now, how we are going to represent it? So, you just see that this are the states, and x1 and x2 are used to represent the states, and you can say that these are used to represent the present state. Then we are going to use next state variable as well, x1 prime and x2 prime. X1 prime is corresponds to variable x1 and x2 prime corresponds to the variable x2. Now, with the help of these particular 4 variables, we are going to represent those particular transitions. So, how we are going to say these things? Now, just say that now already I have said that this is your transition T1. So, this is transition T1 is nothing but from S0 to S1. Okay. Now, what is your S0? I am saying that S0 is your x1 prime, x1 bar, x2 bar, and it is going to next state as your S1. S1 is represented by x1 bar, x2. Okay. So, that means we can say that this is your transition I am going to represent x1 prime bar and x2 prime. Okay. So, you just see that with the help of this combination I am going to represent this particular transition T1. So, this is transition T2. Now, I can say that transition T2 is nothing but it is going from S1 to S4. S1 to S4. Now, what is your S1? This is your x1 bar, x2 and x4 I am representing, sorry, this is your S1 to S3. S3 is represented by x1 and x2. That means, this is a next state variable will be represented by prime version x1 prime and x2 prime. So, like that I can have a transition like T3, T4 and T5. Now, all those particular transition, all those 5 transition will be represented with the help of summation of those particular things. That means, T1 plus T2 plus T3 plus T4 plus T5. So, these are the 5 transition that we are having in this particular transition. So, this expression is going to represent this particular transition behavior, and already I have seen that now T 1 is represented, transition T 1 will be represented by x 1 bar, x 2 bar, x 1 prime bar, x 2 prime plus x 1 bar, x 2, x 1 prime, x 2 prime, like that I can write the expression. Now, you just see that collection of those particular transition is going to give me the behavior of this particular transition system. That means, now see what we have seen, that again all those particular transition can be represented with the help of a Boolean expression. We are getting a Boolean expression. Once we have this particular Boolean expression, then what we can do? We can construct the BDDs for this particular Boolean expression, and once we have this particular Boolean expression, we can use the reduce algorithm to get the reduced binary decision diagram. And if we stick to a particular variable ordering, then we are going to get an ordered binary decision diagram. So, ultimately we are going to get the reduced ordered binary decision diagram of this particular state transition system. So, in this particular case, I can say that I can use the variable ordering as your x 1, x 2, x 1 prime, x 2 prime. I can take this particular variable ordering also. If I am going to take this particular variable ordering, then what we will get? We will get an ordered binary decision diagram of this particular Boolean expression, and once we are getting the ordered binary decision of this particular Boolean expression, then what we can say that we are representing the state transition behavior of my system with the help of this particular ordered binary decision diagram. After that, if we apply the reduce algorithm to that particular BDDs, ordered BDDs, we are going to get ROBDDs of that particular transition system. That means, what we can say that ROBDD can be used to represent state transition diagram. Okay. So, that is why we are saying that state transition system can be represented by Boolean expression. Already we have seen how we are going to represent this particular state transition system with the help of Boolean expression. This is nothing but the combination of all those particular transition, and once we are having that particular Boolean expression, then OBDDs can be used to represent those particular Boolean expression. That means, eventually you can say that OBDDs can be used to represent the state transition diagram. That means, the behavior of our state transition system has been represented by our ordered binary decision diagram, and once we reduce it, then we can say that ROBDDs is used to represent this particular state transition diagram. And if we stick to one particular variable ordering, then we are going to get an unique representation of that particular state transition diagram. Okay, now, we have seen or we have discussed a particular data structure called BDD, binary decision diagram, and eventually we have come up to reduced order binary decision diagram. With the help of this particular BDDs, what we can do? We can represent any Boolean expression, and eventually we have seen that this particular ROBDDs can be used to represent any state transition diagram, because if we are having a sequential circuit, the sequential circuit can be represented with the help of your state transition diagram, and the behavior of state transition diagram can be represented with the help of ROBDD. Now, before that, what we are discussing about? We are talking about a verification technique, and the name of this particular verification technique is your model checking. We have seen this particular verification techniques. It is nothing but a property verification technique, where we are going to represent a particular state transition diagram, or we say that this is a Kripke structure. The property will be represented with the help of CTL, because we have talked about CTL model checker only. We are having other model checker also. So, in model checking system, we are going to use the Kripke structure to represent the states, or represent the transition system or the model of our system, and the Kripke structure is having 3 components. One is your set of states, second one is your transition, and third one is your labeling function. Okay. So, these are the 3 components that we are having. Now, what we are having, the specification and property we are going to represent with the help of your CTL, computational tree logic, because we have discussed about CTL model checker only. And after that, we are having a verification method, in that verification method, what we are going to see basically what we are doing it, we are going to check whether this particular given CTL property is true in this particular model of the system or not. Okay, now, when we talk about this particular model seeking algorithm, what we have seen that this is nothing but a graph traversal algorithm. Okay, because we are having the entire state space Kripke structure, and Kripke structure can be viewed as a graph. It is a simple graph only. So, and we are having a graph traversal algorithm to find out the state of states where a particular given property is true. But we have seen one problem with this particular model checking, which is your graph based model checker. It is having the problem with the state explosion problem, because already we have seen that the number of states are related to the number of states variable we have. So, if we are having n variables or n state variable, then we are going to get 2 to the power n different states. Okay. These are different possible combination that we may have, and these are the different states that we may have, but in particular all states may not be reachable. But in my design, say it requires another one variable. That means, if I say that I cannot do it n variables, I need n plus 1 variable. So, in that particular case, the number of states we are going to get about 2 to the power n plus 1. That means, the number of states is exponential in nature with respect to the state variables. So, this is a major problem if we go for a bigger system, that the state space will be very high. Now, how to contain this particular state space? So, this BDDs can be used to contain this particular state space explosion problem, because already we have seen that the state transition system can be represented with the help of ROBDDs, and in most of the cases we have seen that most of the Boolean expression can be represented with the help of a compact ROBDDs. Also, I have mentioned that the size of this ROBDD depends on the variable ordering. For a particular variable ordering, we may get a very compact representation, but with for the same function with different variable ordering, we may not get a compact representation, it may be a bigger one. Also, to find out the appropriate variable ordering is a hard problem. We do not have any algorithm which will say that this particular variable ordering will give you the best representation, best ROBDD representation for this particular Boolean function. So, this is a hard problem. So, we use some heuristic to get some reasonable some variable ordering which will give us a reasonable size of ROBDD. So, that OBDDs can be used to state transition system, but in our Kripke structure we are having another component which is your labeling function. Now, how we are going to represent this particular labeling function. Okay. No, just see whether I am having slide or not. Okay. So, in this particular case what will happen, you just see that how I am going to keep this particular labeling function. So, consider one particular state transition system, say this is S0, say just I am working this thing. So, this is a Kripke structure, say P, Q. Now, you just see that in this particular state transition system as a Kripke structure, I am having two these things atomic proposition, that set of atomic proposition is your P and Q, and it is having 4 states. S is having 4 states, S0, S1, S2, S3. Okay. And on the other hand, these are labeled with this particular atomic proposition. So, when we talk about Kripke structure, we need the state transition system along with this particular labeling function. Now, when we are using OBDDs to represent the state transition system, along with that we must have the information of this particular labeling function, then only model checking, or you can say that ROBDDs can be used for model checking algorithm. So, in this particular case, now you just see that which are the states where this particular atomic proposition P is true. So, if you see these things, then this is your S0, S2 and S3, and which are the states where this particular atomic proposition Q is true. Then in this particular case, you will find that this is your S1 and S 2. And we know the state transition system that here we are having, say, this is the transition, and what are the transition? I can say that this is S 0 to S 1, S 0 to S 2, like that, S 1 to S 2, like that. You can list all those particular transition 1, 2, 3, 4, 5, 6. So, these are the information we have. Now, this is a subset. This subset can be represented with the help of BDDs, that I can say that this is the BDD representation of those particular states where this particular atomic proportion P is 2. Now, I can represent these particular sets, okay, with the help of another BDD. I can say this is the BDD BQ, which represent the set of states where this particular atomic proportion Q is 2. And these are the state transition that we have in our system, and already we have seen how to represent this particular transition behavior of the system with the help of ROBDDs. So, I can say that this is your B arrow is the ROBDD representation of this particular transition relation. And you just think that it is, if I am talking about the order BDDs, all these BDDs are having computable variable order. Now, what I can say that for Kripke structure, we should have the state transition behavior, and along with that we must have the labeling function. So, that means we can say that B arrow, BP and BQ, these three BDDs is going to represent my this Kripke structure. Okay. So, if I am having this particular Kripke structure, that state transition diagram along with this particular labeling function. So, this information can be captured with the help of these three BDDs. Now, you just see that means ROBDDs can be used to represent Kripke structure also. So, once we represent the Kripke structure with the help of ROBDD, now we will see whether that model checking algorithm can be performed with the help of these ROBDDs or not. Because already we know that if I am representing this Kripke structure with the help of a graph, then I can use some graph traversal algorithm to implement our model checking algorithm and to find out which are the states that a particular property is true. So, this is the graph theoretical algorithm we are using. So, since we are using this particular Kripke BDDs to represent this Kripke structure, now whether can I use this particular ROBDD representation to come up with some model checking algorithm. So, in this particular case it is possible, and we are going to say this is your symbolic model checking. So, if OBDDs are used to implement our model checking algorithm, then we said this is the symbolic model checking algorithm, and we are giving the term symbolic because here the state transition diagram has been represented symbolically with the help of ROBDDs, and set of states, I am going to have a combination of set of states S 0, S 1, S 2 like that. This particular set of states again represented with the help of an ROBDD. You can say that this is a symbolic representation of this particular subset. That is why people are using this particular term symbolic model checking. So, symbolic model checking is nothing but your model checking algorithm only, but here we are using the data structure BDDs to represent our entire state transition diagram. That means, we are using that ROBDDs to represent our Kripke structure. Now, we are going to see how we are going to implement our model checking algorithm with the help of those particular ROBDDs. Now, you just see that I am copying up this particular, already we have discussed about this particular temporal operator AFP, because already we know that we are having some operators, say next state, future, globally and until, and along with that we are having two path quantifiers. So, in all path AX, AF, AG and AU, until operator is a binary operator, but X, F and G are your unary operator, and another path quantifier E we are having EX, EF, EG, EU. Now, we need the procedure to evaluate this particular operator, but already we have seen that we need three operators, which are the adequate set of operators. At least it should contain one next state operator, one until operator, and we can choose one of the operator like F or G, either AG. So, already we have discussed this particular operator AFP, and we have seen how we are going to evaluate this particular AFP. We are having the algorithm to evaluate this particular temporal operator AFP. So, in a nutshell, how we are going to do? If any state S is labeled with P, then label it with AFP. Then we are going to repeat this procedure, label any state with AFP if all successor states are labeled with AFP until there is no sense. Now, you just see that we are starting from some state. If it is labeled with P, I is going to say that AFP is 2 over there. Then we are going to find out all the predecessor of this particular state. Okay. If this all the predecessor state also, we say that AFP is true, because in future we are going to get some state if all the successors are having labeled with AFP. Okay. So, this is the way that we are going to do find out this particular operator AFP, which is your graph traversal algorithm. So, basically what is our basic requirement? If you look into the answer, find a predecessor state of a state or a set of states. So, basically you just see that if I am going to have this particular transition system, okay. Now, say if this is your P and P is true, then in this two case I am going to say that AFP is true. Now, what I am going to see? I am going to see the predecessor. So, from this particular predecessor I will say that AFP is true over here, AFP is true over here. Now, in this particular case, this predecessor is having only one successor, AFP is true. So, I am going to label it with AFP. Okay. Now, for this particular state, since both the successors are having AFP, so I am going to label it with AFP. Now, when I come to these things, I will find that one is labeled with AFP, but second one is not labeled with AFP. So, we are not going to label with AFP. So, you just see that in this particular method what happens? We have to find out the predecessor states of a particular set of states or a particular state, and depending on our criteria, we are going to say that one particular CTL formula is true on this particular states or not. So, in our graph traversal algorithm, so basic requirement is to find out the predecessor state of a particular state or a particular set of states. Okay. Now, for that, now when we are going to look for this particular symbolic model checking, that means we need two operators. One, we are going to say that pre dr exists x and pre for all x. So, these are the two operators we will be needing, pre dr exists x and pre for all x, where x is a set of states. So, what we are going to say that pre dr exists x. Now, we take a subset x of state S and return the set of states which can make a transition into x. Okay. So, we are having a subset x, we are going to set of states which can make a transition to this particular subset, and pre for L x, it is similar to pre dr exists x, but in this particular case we are going to take those particular states which can make a transition only into, this is the crux, transition only into, and here we can say that make a transition into x. So, dr exists, if at least one transition is coming to x, I can say that there exists a transition which is going to this particular subset x. That means, if I am giving a subset x, then we are going to find out the predecessor state of those particular subset x, where at least one transition is coming to this particular states. But when we talk about pre for all x, that means, we are going to consider those states which are going to make a transition to this particular subset x only. That means, all transitions should go to this particular x. So, that is why we are saying that make a transition only into x, it should not go to this. So, our in model seeking algorithm, our basic requirement is to find out the predecessor state, and we can find out this particular predecessor state with the help of these two operators pre dr exists x and pre for all x. Now, this is basically in our material notation, we can say that pre dr exists x, we are going to collect all those particular states belongs to x, such that dr exists a state as that, and we are having a transition from S to S dash, and S dash belongs to x. And for P for all x, we are going to collect all states from S, which are member of this given entire state space, where for all S dash, if we are having a transition from S to S dash, then S dash must belongs to x. So, this is your for all transition must go to x, there exists at least one transition must go to x. So, these are the pre for all x and pre there exists x, and basically these two operators is going to give me the predecessor state of a given set of states. Okay. Now, just see this is a symbol example, just whatever we are talking about pre there exists x and pre for all x. Now, in this particular case, this is a substate we are considering. So, this is your x it is having this particular state. Now, we are going to look for basically we are going to evaluate the predecessor state in such a way that at least one transition will come to this particular x subset x, or pre for all x, all the transition will come to this particular state. So, in this particular case, if you say that pre for all x, then you will find this particular state say S 1, S 2, S 3. So, for S 2 we are having two transition, both the transition are coming to this particular substate x. So, basically it is going to say me that this is your this is x I am writing, say x 2 is the states which are all the transitions are coming to this particular, and pre there exists at least one transition must come to these things. So, in this particular case, since all are coming, so pre there exists x also I am having that x 2. When I come to this particular x 3 state, then you will find that it is having two transition, at least one is coming to this particular subset x. So, x 2 x 3 is going to give me the set of states where it is satisfying that pre there exists x. Okay, so, these are the things that we will be needing over here. Now, you just see that we are having this particular two operator pre there exists x and pre for all x. With the help of these things, we can find out the predecessor states. Okay. Now, here when we are going to look calculating this particular predecessor state, and we know that these are required to evaluate our model seeking algorithm, because already we have seen this particular process where we are going to say that in such type of scenario that at least we have to calculate the predecessor state and we are going to collect all those particular things. Now, we are saying that with pre for all x and pre there exists x, we can evaluate those particular states where in pre for all x, all the transitions are coming to this particular subset x, and pre there exists x, at least one transition is coming to this particular set of states. Now, we are having a relationship between these two things, pre there exists x and pre for all x. Now, this is the importance relationship between pre there exists x and pre for all x. Now, this is now pre for all x can be represented with the help of pre there exists x, and this is the relationship pre for all x equal to s minus pre there exists s minus x, where s is the set of all state and x is the subset of x. Okay. Now, what we can see that how we are going to have this thing, say pre for all x is equal to s minus pre there exists s minus x. Now, say I am having a given set of states, say s is equal to, say I am having s 0, s 1, s 2, s 3, s 4. Okay. Now, say that I am having a subset x which is having, say s 0 and s 1. Now, in this particular case, if I am having s 0 and s 1 x like that, then what is my s minus x? S minus x is basically S 2, S 3, S 4. Okay. Now, you just see that if I am going to evaluate for pre for all x, then what will happen? I am going to consider all those predecessor states where all the transition is coming to this particular two states S 0 and S 1. This x is the set of states S 0 and S 1. So, pre for all x, in this particular case, all transition must come to this particular states. Now, I am going to take the set difference, I am going to look for s minus x. So, s 2, s 3, s 4 is the set of states which represent s minus x. Now, when I am going to consider that pre there exists s minus x. So, in this particular case what will happen, from a particular state at least one transition is coming to this particular s minus x. So, you just see that if for a particular state, if one transition is going to s minus x, that means all transition will cannot go to this particular x. Just see that. So, this is my set of state x, and the other portion is basically I am having this is minus s minus x. Now, if I consider one particular set, say S n. Okay. Now, if one of the transition is coming to say this is say S m, which is not belongs to your x, that means S m is not belongs to your x. That means at least we are having one transition which is not going to this particular x. Okay. So, this is the things that I am getting. This transition I am going to look for pre dr exists s minus x. So, this particular state will not come under pre for all x, okay, because all transitions are not going to x. So, that is why what we are doing, first we are evaluating pre dr exists s minus x. So, such type of things we are getting, and that means such type of state S n will come into picture, and it should not be included in pre for all x. So, in this particular case I am evaluating these particular things, and eventually I am removing those particular states from S, at least where transition is at least one transition is going outside of this particular x. So, the remaining set will be remaining state is going to give me pre for all x. Okay. So, in this particular case what will happen, you just see that here we are evaluating pre for all x with the help of pre dr exists s minus x. Okay. This is the way that we are going to evaluate. That means, if we are having a procedure for pre dr exists x, then from here we can always evaluate pre for all x. That means, you just see that we need one procedure which is going to evaluate pre dr exists x, then very well we can calculate pre for all x. Okay. So, that is why what happens, now we just see that the whole transition system we can represent with the help of ROBDDs. If we are having a subset of x, it can also be represented by ROBDDs. Now, we have to see how we are going to evaluate this particular predecessor step. Okay. Already we have seen that we can, if I can get a procedure for pre dr exists x, okay, it is going to give me all the steps from which at least one transition is coming to this particular subset x. Now, once we have this particular procedure, I can always calculate pre for all x, because we know the relationship pre for all x is equal to s minus pre dr exists s minus x. So, if I am having a procedure for pre dr exists x, we can evaluate pre for all x. Now, how to evaluate these things? Now, in this particular case, now we are going to, today I am going to stop here. In next class, I am going to say how we are going to evaluate pre dr exists x, and once we can have the procedure for this particular pre dr exists x, then what happens? We can evaluate pre for all x also, and once we have this particular procedure, then we will see how we are going to implement our model checking algorithm with the help of this particular ROBDDs. That means, we are going to represent our transition system with the help of ROBDDs, okay. And now we are going to implement those particular model checking algorithm with the help of this particular ROBDDs, and in this particular case we are going to say this is the symbolic model checking algorithm. Okay. Now, just look into a question that I am saying that draw the state transition diagram of mod 6 counter. So, what you have to do? Give a binary encoding of the states, give the Boolean expression for this transition system, and indicate the labeling function. Okay, we have to indicate the labeling function. Which are the labeling function? Now, how we are going to say? I am talking about a mod 6 function. So, mod 6 counter basically. So, it will count from 0 to 5, again reset to 0. That means, what happens? I can say that if this is your 0, then I am going to have 1, then I am going to have 2, then I am going to have 3, 4, sorry, 5, 5, then again it will go back to 0. That means, how many steps we are having? 6 steps we are having. That means, we need how many state variable will be needed for it? This is your log 6 to the base 2 ceiling. So, that means, we need 3 variables. So, I can say that x 1, x 2, x 3 are the 3 variables, and what let us say, if I say that this is my state S 0, S 1, S 2, S 3, S 4, S 5, then I can say that S 0 state at cooling will be your 0 0 0, S 1 will be your 0 0 1, S 2 will be 0 1 0, like that. These are the state at coding. Now, what I am saying that first you have to say, give the binary encoding of the states. This is the binary encoding. Give the Boolean expression for the state transition system. Now, what will happen? Now, what are the state transition? You can say that I am having a transition from S 0 to S 1. Now, since to represent this particular transition behavior, I need another set of variables, then I can say that x 1 prime, x 2 prime, x 3 prime. So, this transition from S 0 to S 1 can be represented with the help of x 1 bar, x 2 bar, x 3 bar. This is 0 0 to 0 1, x 1 prime bar, x 2 prime bar, x 3 prime. So, this is the transition behavior for this particular expression for this particular transition. Similarly, for the second transition also I can represent, it is going from S 0, S 1 to S 2. Like that, I can represent all those particular 6 transition with the help of this particular 6 variable x 1, x 2, x 3, x 1 prime, x 2 prime, x 3 prime, and we can have a now Boolean expression for those particular state transition diagram. Now, indicate the labeling function. Now, when I am going to talk about this particular transition behavior, then you will find that x 1, x 2, x 3 all are 0, that means, all are false. Here in S 1, I am going to say that this is labeled with x 3, this is labeled with x 2, because what happens, I can say that this is nothing but x 1 prime, x 2 prime, x 3, this is 0 0 1. That means, x 3 is true in this particular state S 1. So, that means, what I can say that it is labeled with x 3. Similarly, it is labeled with your x 2, and I can say that this is labeled with your x 2, x 3, like that we can have the label. And already I have seen that if I have the label, now I will be knowing which are the states that x 1 is true. Now, you can collect those particular states, and we can represent this particular state with the help of ROBDs. So, that is why I am saying that indicate the labeling function. So, this is the way we are going to do it. Secondly, we are going to say that consider a microwave oven controller and give the state encoding. What is the Boolean expression for the state transition diagram? So, this is another question that already we have discussed about this particular microwave oven controller, and we are having the state transition diagram. So, this is the state transition diagram that we have. Now, in this particular case, I am having 4 state variables. So, I can say that start. So, I am going to say that represent start by S, then I am having close. I am going to have this particular C representing this particular close. Heat, I can say that H is my heat representing answer, error E. Say E, I am going to represent error by E. So, these are the 4 state variable I will be needing to represent this particular state. Now, when I say that what is the binary encoding of this particular state, I can say that it is labeled with basically S bar, C bar, H bar, and E bar. Similarly, when I say that what is the state encoding of this particular state, I can say that this is start is true, close is true, heat is true, but error is false. So, these are the state encoding. So, similarly, when I come to this particular state, what is the state encoding? I can say that this is start is true, close is true, heat is false, error is false. So, these are the state encoding. So, what I am saying that consider a microwave oven controller and give the state encoding. So, I can have the state encoding. What is the Boolean expression for the state transition diagram? Now, in this particular case, now you have to consider all those particular transitions. I am having this particular transition, it is going from, now we need another set of variables where I can say that the next state variable will be your S prime, C prime, H prime and E prime. So, this particular transition I can represent is like that, it is going from S bar, C bar, H bar, E bar to S close bar, H bar and E. Okay. So, this is the present state, this is the next state. So, this particular transition is represented with the help of this particular Boolean expression. Like that I can write the expression for all those particular transition and eventually I can get an Boolean expression. So, that is why I am saying that what is the Boolean expression for the state transition diagram. We can get the Boolean expression for the state transition diagram, and once we get it, then what we can do? We can represent this particular Boolean expression with the help of OBDDs. Okay. Today I will stop here. In next class, we are going to see how we are going to evaluate pre-DRXG text, and with the help of that operator, we are going to see how we are going to implement the model checking algorithm using PDDs. Okay, and that means we are going to get the algorithm or method for symbolic model checking algorithm. Thank you and bye bye.